Section 3.7, Elasticity of Demand. This will tie back a little bit to that last section where we were talking about revenue functions, right? Maximizing revenue, that idea. So there's a little bit of tie back to what we had talked about in that section. So we'll review a little bit of that and carry it forward. So first question I have, how does a company decide on the price of a product? All right, I mean, we've kind of discussed that on many different occasions, even, back when we were in class. And there's a lot of factors, there's a lot of variables that go into doing that calculation, right? So how much are they going to charge for a particular product? But essentially, the main, I think, component of the main factor of that would simply be the demand for the product, right? If we charge a particular price, are people going to pay that price for the product, right? So what's the demand from the consumer at the price given? So if they're basically it's the whole thing. What are they charging for it? Well, they're going to charge what you're willing to pay, right? And as long as we're willing to pay some stupid price for some menial item, then we pay a stupid price for a menial item, right? So that's primarily the dictator. Of course, there's other things that go into play right there. There's a lot of different factors involved, but that's I think the primary one. So if a price is increased, right, demand typically is going to decrease, right? So if you sell or raise the price on a product at some point, right, demand for that item is going to decrease because people are just simply not going to pay what you're asking. But the other side of that is, and this is what we talked a little bit about in the last section, how does that affect your revenue? Right? We had an example, remember, with the theater and the number of attendees at a certain price per ticket. And we actually saw that by decreasing or by increasing the price, we had a decrease in demand because there were fewer attendees, but the revenue went up, right? And since we said before, I think the main objective for most companies, not exclusively, but most companies, I think, or most businesses, they're trying to maximize their profit, right? They're trying to bring in as much revenue as possible so that they can maximize their profit. Now, revenue and profit, are those necessarily the same? We've talked about, does max revenue mean max profit? Nah, not necessarily, right? But there's a lot of different things that go into that. But we're going to focus on revenue at this point, right? So revenue may increase even though the demand decreases, right? But at some point, you increase the price, demand is typically going to decrease. So what price can be charged to maximize revenue, right? So that was, again, the kind of question we were interested in the last section. That's what we're interested in here. So I want to maximize revenue. What's the price that I can charge for my product so that I can maximize the amount of revenue that we take in on that product? Now, again, is that the same as max profit? Not necessarily. And I think for the majority of discussions, probably, but not necessarily. That's another question. Again, for you business majors, y'all can explore that moving forward. A demand function. Now, we talked about demand functions in the last section. We called it a price function at that point. Uh, the price that's charged for the particular item and how much you would expect to sell at that price. There's different notations that are used here, so be careful here. We call it Q or D of X. Right? This is what we're calling a demand function. And it relates the quantity, that's the reason for the letter Q, the quantity of units purchased to the price X in dollars per unit, or whatever the price happens to be. It doesn't necessarily have to be dollars, but most of the time that is the case. So it's a relationship between the amount or the quantity, or the amount of the quantity purchased to the price X. So we call that the demand, right? How much of the quantity are you going to sell? It depends on the demand for the item. Right? So call that your demand function, or the quantity. And then is your price. Now, this is usually a decreasing function, right? Because like we said, if you increase the number or the price of the product, typically your demand or the amount or the quantity is going to decrease at some point, right? And so from that point forward, you're always going to lower the amount sold if you increase the price. Now, there's two different things that can happen. This is what we were talking about with revenue. So let's say there's a slight increase in price. All right, that's kind of what we looked at in that last section. Two things can happen. we could have a slight decrease in the demand, right? So we increase the price, the demand is going to go down a bit. But yet the revenue still increases. That's what happened with our ticket sales for the theater. But here's the other side of that. What if by raising that price by a little bit, we get a large decrease in demand? So I mean, maybe we've reached that point of what people are actually willing to pay for our product. And so if we raise the price a little bit more, the demand drops drastically, so much so that now even revenue decreases, right? So, we always talk about, we say with that, we're always looking for that sweet spot. You know, I know what price is going to cause revenue to increase. I know what price would cause revenue to decrease. What's the price that's going to maximize my revenue, right? What's the sweet spot on revenue to bring in the most? To measure this sensitivity of demand in these small increases of price, economists calculate what is called this elasticity of demand, and that's what we're exploring in this case. So the elasticity of demand is what's happening, what's the relationship between the demand and that increase in price, or how does the increase in price affect the demand? So for example, and this is kind of a little basic example, and I'll get into more interesting examples as we go forward. But let's say I have a demand function for a product. Q, or D of X, equals 120 minus 20X. Right? That's our demand function. Q is the number of items sold at a price of X dollars. And let's say we charge a price of $2. Right? So X is $2. What is my demand? How many units would be sold at that price? Right? So our demand at $2, D of 2, we would expect to sell 80 units. What would our revenue be? This out of my way. Our revenue, if we're going to sell 80 units at $2 a piece, then our revenue would be 80 times 2, or $160. Well, let's increase our price. Let's increase X to $2.20. What would be our demand, or what would be the amount that we would expect to sell at $2.20? So D of 2.2 drops us down to 76 units, right? So we had a decrease in the demand from 80 to 76 units. But what happened to revenue? Well, we're selling 76 units, but at $2.20 a piece, we have total revenues of $167.20. So even though our demand decreased from 80 to 76 units, our revenue actually went up $7.20, right? Let's say instead we were charging $5 per unit. At $5 per unit, we had a demand, plugging that into our demand function, same function, D of X above. We have a demand for 20 units. And our revenue, since we're selling 20 units at $5 a piece, is $100. Okay. So then let's change our price. Let's raise it from 5 to $5.50, an increase of 50 cents. So at $5.50, our demand, according to the demand function, drops to 10 units. Right? So again, we have a decrease in demand. That makes sense. We increased the price, the demand decreased. But look at what happened with revenue this time. At $5.50, selling only 10 units, we brought in $55. Even though we only had a 50-cent increase in the price, small increase, the revenue almost dropped by half, right? The revenue went from $100 to $55, almost cut in half. So there was a drastic decrease in revenue. So this is what we were talking about earlier. So maybe at a point I can increase the price but still have an increase in revenue. But I could also get a decrease in revenue. And we're interested in, okay, well, where's the profit? Where's the price that would give us the maximum revenue? All right? Like I said, I called it the sweet spot. Where's my sweet spot in price? All right, here's a definition. There's this elasticity of demand that we were talking about. We're going to call this E. E for elasticity, real original. It's given as a function of price, represented by X, and the demand function, D of X, where E of X is equal to the negative of X times D prime of X over D of X. Now, I'll spare you the derivation of that formula. I'll let you You know, if you're interested and you want to read the textbook, you can see exactly where that formula came from. All right, but all I care about is that you know how to use it. So we'll call this the elasticity of demand function, this E of X. Now, the reason for that negative in front, just to kind of clarify as far as why this thing looks the way it does, well, remember X represents the price of our item. All right, so that's going to be a positive value. Remember, D of X is the demand, how many of the items we would expect to sell at that given price. So that, again, should be a positive value. Right? We're not going to sell negative items. The derivative of our demand function, D prime, we said is usually going to be a negative value. It's going to be decreasing. Our demand decreases as you increase the X value, right? So D prime should be negative. So if X is positive and D of X is positive and then D prime is negative, if we throw an extra negative in front of that fraction, that'll make the whole thing positive. So that way you get a positive value for your elasticity of demand. All right, so that's the reason it looks the way that it looks. But again, if you're interested in where that function comes from, feel free to read through the textbook in that chapter or that section. Knock yourself out. Now, there are three possible cases. There are three possibilities as far as the value for that elasticity of demand, the value for E. If E of X, if the value of that function is less than 1 for a given value of X, the demand in this case is said to be inelastic. Right? So inelastic demand. This tells us that a small increase in price will result in an increase in total revenue. Right? So like we had in that first case of the example we just looked at when we went from $2 to $2.20, that small increase in price still gave us an increase in total revenue. That is described as being inelastic demand. If, however, E of X is greater than 1 for a given value of X, then demand is said to be elastic. That's the case where a small rise in price will result in a decrease in revenue. That's what happened in the second case where we raised it from $5 to $5.50. The third possibility, though, is what if your elasticity of demand is equal to 1? This is the case where total revenue is maximized. We call this unit elasticity. Right? And ultimately, that's what you're interested in, right? I want to know where we can maximize revenue. Because, we said typically that means maximum profit, not exclusively. There's my disclaimer on that. But usually we want to know where we're going to maximize revenue. So that's called unit elasticity, and that's where E of X equals 1. This is followed by a theorem, right, which kind of ties in with that, and what we were talking about earlier. The total revenue would be increasing if X value, or at any X value for which E of X is less than 1. Because if E of X elasticity is less than 1, we said revenue is increasing, right? Total revenue is decreasing at any X value for which E of X is greater than 1. So that was number 2 above, where we have elastic demand. Right, so revenue is decreasing for values of E that are greater than 1. And total revenue is maximized at the value or values, there could be multiple values for X, for which E of X equals 1, right? So that was our unit elasticity. We said we're looking for that value of X that's going to maximize our revenue. Okay. This kind of gives you a little graphical representation. You may find this a little bit useful in helping in kind of picture what's going on here. We're talking about two different functions, all right? We're talking about that demand function, D of X, and that revenue function, R of X. So on the left, we've got Q equals D of X, our demand function, which we said as X increases, right? As we increase X, the demand decreases, right? D of X goes down. Here's that sweet spot. Here's our unit elasticity. What value of X, how many units, or what price, could we charge to hit this sweet spot to where demand goes from being inelastic to elastic? Now, what does that mean again? Inelastic demand means revenue is still increasing. Elastic demand means revenue is decreasing. So we want this sweet spot to tell us at what point does revenue change from increasing to decreasing? Where is it maximized, right? On the right, we have our revenue function. So notice again, revenue here is increasing on the left side of our unit elasticity, where E equals 1, increasing revenue. And then it's decreasing on this side, right, where we have elastic demand, or where E is greater than 1. Right, so it kind of gives you a little bit of a visual as far as, because we're talking about two different functions, so it's kind of easy to confuse or get kind of backwards as far as what each of these is telling me, right? So the demand function is decreasing, and then we have that effect on revenue from increasing to decreasing at that point of unit elasticity, and that's typically the point that we're interested in. So now there's going to be actually two ways that we can find that, right? Because I know that this unit elasticity occurs where E equals 1. So if I can develop my elasticity function, E of x, then I can set that equal to 1 and solve that equation to find this guy. We also can find it using our revenue function, and that's what we did in the last section, right? I mean, I can find where my revenue function is increasing and decreasing. We can find those critical values, and there's the location of our maximum revenue. And so we actually have two different ways that we can now do this. I'll do you an example, maybe show you both ways. So it's not a new concept. It's just how we're doing it, or how we're finding it. So let's say, for example, now, so this elasticity of demand thing, it's a pretty straightforward concept. The whole thing is coming up with E of x, with the formula, with the equation. But once we have that function for E of x, then it's just a matter of evaluating it and observing the outcome. So let's say, for example, from that previous one that we looked at, the little simple example, where we have that demand function of d of x equals 120 minus 20x, right, that original one. And again, that was our Q also. So again, you see both notations used, Q or d of x. Find the elasticity of demand, right? So elasticity of demand, E of x, is that negative x times d prime of x over d of x. So first I need d prime. And again, that's a simple little linear function. So d prime is negative 20. So here's E of x equals negative x times negative 20 over d of x, which is 120 minus 20x. And then all I did from there is simplify. I've got the two negatives to give me a positive 20x over 120 minus 20x. And then I factored out the 20 in the denominator and divided out the 20 to give us E of x equal to x over 6 minus x. So that was just simplification once I plugged it into the formula. And then we can evaluate E of x for the different values that we looked at, right? So first find the elasticity at x equals 2 and x equals 5. Remember, those were the two values that we had, $2 and $5. So if I take 2, plug it into E of 2, it'll be 2 over 6 minus 2, 2/4, or 1/2. So that gives me a value for E of 1/2, which is less than 1. And we said for elasticity, if E is less than 1, you have inelastic demand, which means revenue should be increasing. And if you remember, at that point, we increased by 20 cents, but we still had an increase in revenue at that point. So we showed that a small increase in price still gave us an increase in revenue. That's inelastic demand. For E of 5, right, we had the second scenario where we charged $5. So I plug 5 into E, and I get 5 over 1, or 5, which is greater than 1. And so the value of E there being greater than 1 means we have elastic demand. And that's what we saw in our example, that when we raised the price from $5 to $5.50, we had a decrease in revenue. There was a big decrease in revenue relative to the situation, but it was a decrease in revenue. So that's elastic demand. Question part C, I want to find that sweet spot. I want to find the value of x for which E of x is equal to 1. I want to find that value that would give us unit elasticity, which is the maximum, or the point of maximum revenue. So again, I'm taking E of x, and I said, okay, well, let's just set that equal to 1. That's one way that we can do it. because I know that's where unit elasticity occurs. And then we're just solving that equation. So I multiplied both sides by 6 minus x, solve for x, and I got x equals 3. So this is our point of unit elasticity. Unit elasticity occurs at a price of $3. We said that tells us where revenue is maximized. Right? So at a price of $3 per unit, we could also then calculate the demand for the units. Right, remember that goes our demand function originally was 120 minus 20x. So just plugging 3 into D, I've got D of 3, gives us a demand for 60 units. And then we can calculate our revenue if we sell 60 units at $3 a piece. We've got revenue of $180. All right. So yeah, it's maximizing revenue, finding where revenue is maximized, but using the elasticity function in this case. Here's another example, a little more interesting. The world demand for oil is given by this function Q or D of x, where x is between 0 and 180. Q in this case is measured in millions of barrels of oil per day at a price of X dollars per barrel. So I've got millions of barrels of oil per day at a price of X dollars per barrel, and there's our demand function. Right? How many barrels of oil would we expect to sell? Right? What's the demand? So question for part A, find the elasticity. Right? So that's our E of x equals negative x times d prime of x over d of x. So we'll start finding d prime. Again, nice little power function. So there's d prime. Plug that into our elasticity formula. And then we simplified. So we then distributed the x, the negative, and then just rewrote it. I put the numerator back so where the first term was positive. But ultimately, there is E of x. There is our elasticity of demand function, number of millions of barrels of oil per day at a price of X dollars. Question part B. Find the elasticity at a price of $75, $100, $150 per barrel and state whether demand is elastic or inelastic at each price. Right? So again, that's just evaluation, right? I found the elasticity of demand function above, and we're just plugging in values for x. At $75, we have a value of 0.2. At $100, we have a value of 0.6. At $150, we have a value of 3.3. And then we're comparing each of those to 1, right? So we said for values that are less than 1, you have inelastic demand. So at $75, demand for oil is inelastic. At $100 per barrel, demand is still inelastic. But at $150, demand is elastic. So there's an increase in revenue for 75 or at 75 or $100. So if it at those prices, if we were to increase the price by just a little bit, revenue would still go up. But at $150, if you would increase the price a little bit, you would expect to see revenue drop. Right? So we know that then somewhere between $100 per barrel and $150 per barrel is that sweet spot, right? We're looking to maximize revenue. So part C, at what price is revenue a maximum? And I tell you now, there were two different ways that we could do that. So I'm going to go ahead and do it both ways here. I mean, you really have your choice because we know revenue is maximized where E of x equals 1. So we could do it that way like we did in the previous example. So we could take E, set it equal to 1, and solve that equation. Now, these are a little more realistic numbers for the real world, so, bigger numbers that you have to work with, but hey, that's real world. So I'm just solving that equation, went ahead and multiplied to clear the fraction, and I ended up with a quadratic equation, so I set that equal to 0, and yeah, quadratic equation. Let's solve it using quadratic formula. Right? I mean, if you want to try to factor that, knock yourself out. But you can always use quadratic formula. So that's all I did, plugged it in. Maybe just a couple of reminders when you're doing that. So what I did was I approximated the square root because we're in an application. I mean, I want to know, I want a usable value here. So I approximated the square root. And then we had the plus or minus that you have in that numerator. So on the minus side of things, you get this negative 48.3 approximately. And on the positive side of things, 600 plus the 1464.7 divided by 18, you get x equal to $115. Right? Because again, remember, that's your price. Right? This is our elasticity of demand, E of x, where x is the price that we're charging. So we're told by this model that unit elasticity occurs at a price of $115 per barrel. And that is then where maximum revenue would occur. On the right side, I did it using the revenue function. Right, because I mean, we did that initially. We found maximum revenue by developing a revenue function and then finding the critical values and so forth. So recall, revenue comes from what? The price times the number of units sold. Well, in this case, price is X. All right, that's the price that we're charging. And the demand, D of X, that's the number of barrels sold. All right, so X times D of X, price times number of units sold. So we had D of X, our demand function originally. So we just constructed our revenue function by taking X times D of X. Again, I just distributed the X to simplify. This gives us a revenue function. And I want to maximize that revenue function, so let's find our critical values. Find our derivative. Set that derivative equal to 0. And look at the critical values I got. Negative 48 and 115. Which notice were exactly the same values that we got over here. Different context, different process, same result. So X, of course, can't be negative. That doesn't make sense. That's the price. We're not going to charge a negative price for our product. But X could be 115. And like we said, since we're using the revenue function, we want to make sure that that's actually the location of a maximum. So we'll do our little test strip at 115. We could check R of 114. If we wanted to plug in, say, the revenue, we should see that that value would be positive. Not R, but R prime, excuse me. And then we would also check R prime at something on the right of 115, and that should give you a negative value. So we're increasing on the left, decreasing on the right of 115, which means at 115 there's a maximum. Right? That's doing it the way we did it before. So either way, you now have two ways that you can find maximum revenue. You could find your elasticity, set that equal to 1, solve for X, or you could find your revenue function and find the maximum of that revenue for that way. So max revenue is at a price of $115 per barrel. And we could also calculate the demand, right? Because we have our demand function, our quantity that is expected to be sold. We have a demand of 44,825, and that was in millions of barrels per day. And so again, that was just back to that original demand function. I plugged 115 in. Right, so two different ways that you can do that, and luckily we get the same result in both cases, so it makes sense that that works. That is section 3.7.